Hi, welcome back everybody. Today I'm going to talk about how to do a CASSCF calculation on a cobalt porphyrin and how to find the correct active orbitals for a relatively large active space. So this is a cobalt porphyrin with an apical pyridine ligand. So initially I did a DFT calculation. So for this I use PV0 as a functional and SVP basis set on all atoms and T set VP on the cobalt, and I did an optimization in order to obtain a set of orbitals which I can use in the complete active space self-consistent field calculation. And if we go to optimize geometry, tools, render molecular orbitals, I can find the orbitals which are around the HOMO-LUMO gap. So the active space that I'm going to consider has 11 electrons in 9 orbitals, because low spin cobalt has 7 electrons in 5 orbitals, and then there are 4 Gauterman orbitals in the porphyrin with a total of 4 electrons. So that gives 11 electrons and 9 orbitals. So I am going to plot only the alpha orbitals here, and I'm going to plot at least 20 or 30 orbitals around the HOMO-LUMO gap. I will choose a slightly smaller grid so that this is not so slow. Okay, now that the rendering is done, we can see here that I have orbitals from number 210 to 235. Remember always that the Chemcraft will start counting on 1 and ORCA from 0. So we will have to subtract 1 from all these numbers when we type anything into ORCA. So how do we know exactly where the active space is? So this is cobalt 2, low spin. So I have 11 electrons and the spin is 1/2. So that means that the SOMO will be orbital 227, and then I have 5 orbitals until 222 that will contain 2 electrons each. So that will complete the orbitals, the number of orbitals which are occupied in the active space. So the first one is 222 in Chemcraft notation. So if I have 9 orbitals, that's until 230 in the Chemcraft notation. Now I'll go to my input file for the CASSCF calculation, and I wrote down that the active space goes from 221 to 229 because again ORCA starts counting from 0. So this is causes confusion, but it's better to write down as comments which are the active orbitals in the active space. So what I need to do is to read the orbitals from the output file. So I do it using the moimp keyboard and choosing the GBW file. So this means that where I submit the calculation, I will have to have this file on the same folder as my input file. What I have to do is basically go and find the correct orbitals and show the different orbitals. So this is the first one. We see this is not one of the orbitals I want. I want metal-based 3D orbitals, and also want the Gauterman orbitals, which we will see later how they look, and they are centered on the ring. So this one doesn't have what I want. This one may have something, has some 3D metal character, so I will write that down. This one also has a metal 3D character, although small. This one is mainly the DZ² orbital, anti-bound to the pyridine nitrogen. That's a very common pattern for apical pyridine ligands in this type of complexes. So far 223 to 225 are good orbitals. 226 is one of the Goterman orbitals. This is the HOMO -1 of the free base porphyrin. It looks like a relevant orbital. This one we also wanted 227, and this one 228. Remember, and now I was subtracting 1. So, and this would be the last one, which is a pyridine base orbital that we don't want. What we do is write this down. So I wrote that the 223, 224, 25, and 26 have d orbital character, and 227 has a pi orbital character. So 227 is one of the orbitals I want, and I write this also for 228. 229 is not one of the ones we want. So I need to go and find the others. So these three orbitals, 229, 221, and 222, I want to replace them by other orbitals. So I need to go and find them. If I keep going, I see that the orbital 231 in ORCA notation is the dx² minus y² orbital. So I go to the file and say, okay, 231, I will rotate it with 229, which is an orbital I don't want. So in this way, I will be putting the dx² minus y² orbital in the active space. This is an orbital I don't want in the active space. If I go the other way, I can see that this one is a metal orbital, which is a good candidate. 220. 219 is also good candidate, and they are better than 222, for example, but that's relative. If I keep going, this one also could be the XY orbital, 212. And if I keep going, I see that also 209 could contain some XY orbital. What I do here is rotate the 209 orbital with 221 that I don't want. And then, because 219 and 220 look to me at the time to be better XZ and YZ orbitals, I rotate them with 222 and 224. So this will be a test. I don't know if this will give me a better active space, but I have rotated some orbitals into the active space that look like the active orbitals that I want. So then I do the CASSCF calculation. So here I define the settings for the CASSCF calculation. So the number of electrons is 11, the number of orbitals is 9, the multiplicity is 2. And here the number of roots is 60, and these are weights for considering the weight of each root in the state averaged orbital optimization. You should not concern yourselves with this. This is a particular case that I was exploring different options. Probably this is not necessary. These other options are conversions options, max iter to switch comp, a request perturbation theory, and some relativistic properties for G values. The G values will basically tell me if the calculation makes sense because I can compare with experiments. And the geometry is the same geometry that I obtained from the DFT optimization. So now this is the output file from the first CASSCF calculation, which I did from reading the orbitals and rearranging the orbitals of the DFT wave function. So I will render molecular orbitals. In here, the CASSCF orbitals have occupations. The field ones are W occupied, and the active orbitals have occupations between 0 and 2, and the virtual orbitals have occupation of 0. So I will go and see the active space, and I will also add some orbitals before, and I will decrease the quality. So now we can see the active orbitals from the CASSCF calculation. If I go to 221 is the first active orbital, we can see the occupation is lower than 2. Now if I see the surface, it is, although it's a pi type orbital, is not the one we want. This one is also not exactly the one we want. This one is. This one also is a 3D metal orbital. This one also dx squared minus y squared. And this is these are the LUMO plus 1 orbitals. So we are basically missing 2 orbitals here. The dz square, that we kind of lost it, we had it. And one of the porphyrin orbitals. So if we go here, so if I go to even the lowest orbital that I had plotted, I still don't find it. So that's one of the problems with CASSCF calculations. Sometimes the orbitals are hard to find, but we have to keep searching. So what I'm going to do is go again to single point geometry, tools, render molecular orbitals, and I will render a few more. Because I'm missing the dz square orbital, I know that this orbital tends to be it's occupied or partially occupied, so I know that it will be amongst the occupied orbitals and not amongst the virtual orbitals. But if you're not sure, you should search in both directions. So I will untick this delete all cubes, because I want to keep seeing all the cube files that I can. So 210 was the last one, so I will go a few more. Again, show isosurface. This one I don't want it. This one I don't necessarily want it. And here I see something that has some dz square character mixed with the porphyrin, so this could be. And this one I don't want it. So basically this orbital, which in here is 206, but in ORCA notation is 205, contains a certain character of dz square orbital. So I'm going to move this into the active space. So this is another input file. Notice that my code is AC. The previous one that I had been watching was AB, and the original one from DFT was AA. I read the CAS11-9AB wave function, and now I rotate the orbital 205, which was that candidate, into the orbital 221, which was one of the orbitals I didn't want. I didn't write it here, but 222 and 229 are the LUMO plus 1, so they are okay. and the order probably changed here. I did not rewrite which orbital is which, but you should, when you're starting, try to write down which orbital is the XY, which orbital is the XZ, which orbital is the HOMO -1 orbitals of the porphyrin or whatever molecule. You could use comments to give yourself basically a notebook of what you have been doing. So what I wrote here is 205 is the best candidate for DZ square, but it is not very good. And I also wrote I can't find the DZ square orbital, but actually it turned out I did find it. This was good approximation. Then I run basically the same options as before. So this is the output file, but before we're going to look at the orbitals. So we go to ac.out, single point geometry, tools, and I will render the active space orbitals. Okay, so the render is finished. So I look at the orbitals, and this is the HOMO -1 orbital. Then I have the XY orbital, purely metal based. Then this is the HOMO orbital, which has an admixture with the XY orbital. This is the XZ orbital, YZ, C squared orbital, which now it has some anti-bonding with the nitrogen, but not as pronounced as the orbital before, which was outside the active space. CASSCF is self-consistent field, so it optimizes at the same time the molecular orbitals and the coefficients for the different configuration state functions. That's the power of the method. This is the x squared minus y squared, and this is LUMO plus 1. So basically I obtained the correct active space orbitals. So this is probably not the correct ordering of the active orbitals considering some chemical point of view, but actually the ordering of orbitals inside the active space doesn't matter. What matters is the energies of the different states that we get. CASSCF procedure will obtain different states with different energies that have different orbitals occupied. So it doesn't actually matter which order there is. Also, these energies don't matter really. You can use these energies as a guide for selecting orbitals sometimes, but they have no meaning per se, the orbital energies. So now that we saw that the active space orbitals are reasonable, we can look at some numerical results in the output file. So this is the output file. The input file is reproduced here. So here is basically the composition of the different roots, and if I go to the ground state root, I see that the main configuration contains 1 unpaired electron in the 6th orbital out of 9. So which one is the 6th orbital? If I go here, the 6th orbital is DZ squared. So basically the CASSCF calculation is telling me that in the ground state, the DZ squared orbital is the singly occupied molecular orbital. Of course, there are contributions from other electron configurations, but this is the main one, and actually this fits with experiment. It fits with EPR results. So already this is telling us that calculation is reasonable. Then we will have different excitations, and we will see that the first root has a certain excitation towards an electron in probably the XZ orbital or the YZ orbital, and the second root will have an excitation to the other orbital, which is the XZ orbital, and these energy differences are quite reasonable. We can see a lot of other things, and if we go to, so notice that this took 6 hours and 30 minutes, and I was running it on 16 processors. If we go up, we have spin orbit coupling corrected absorption spectra. We are not probably going to see the spectrum of the porphyrin. Cobalt porphyrins have very characteristic solid and Q bands, but very likely the number of roots that we have selected, 60 is not enough. So 60 roots are mainly DD excitations for this system in particular. So we would have to increase maybe to 80, 100 roots to start seeing some good transitions. But what I want to show is the G matrix that we obtain. So what we get is a one G value that's almost 2, and two of them that are 2.37 and 2.38. If we plot that, we will see that these two values are contained in the cobalt porphyrin plane, or the approximate plane, and this value will be pointing perpendicular to the cobalt porphyrin plane. So I know from experimental results on related systems that these values are quite okay. They are not perfect, but they are quite near the experimental values. So basically, this calculation is already giving me a result which is chemically reasonable and spectroscopically reasonable. So it took basically 2 iterations. We started with a DFT calculation, then we read the orbitals into a CASSCF calculation. We rearranged several orbitals, which we had to find some of them kind of far from the initial active space, and this was good but not good enough. So then we had to do a second CASSCF calculation in which we read the results from the first one, and again then only had to rotate one orbital, and then this likely gave us a chemically correct result. The only thing that would remain to improve this result would be to increase the basis set and increase the number of roots in order to see if the UVB's calculated spectrum is close enough to the experimental UVB's spectrum, which is also known for this porphyrin with a bound pyridine. So I hope this has been useful. This is an example of a not so trivial CASSCF calculation. The active space is larger because porphyrins, and the same with other types of ligands, are non-innocent and are redox and spectroscopically active, and therefore their frontier orbitals usually have to be included besides the metal orbitals in order to get a good description of the electronic structure and reproduce some experimental properties. In this case, EPR, but also UVB's properties for sure. So I hope that the procedure of finding the orbitals and rotating them in the active space was clear enough. I recommend that you write down on a piece of paper, even draw or print out the different orbitals when you do a preliminary DFT calculation or a CASSCF calculation, and then you write down exactly which ones are possible candidates for the correct active orbitals, and then try rotating them into the active space. Sometimes it takes a few consecutive CASSCF calculations that get better and better, and then you get a very nice result. So thank you very much. If you found this useful, please subscribe.